Hello everyone, welcome to this course MTH 201. This is the first lecture of this course. So, this course is aimed for the BS second year students and MSc first year students of our department. This is actually designed to be a second course in linear algebra. So, the students who are from BS MS background here, they have done their first linear algebra course in MTH 102, and the students who are joining the institute in MSc program in MSc first year, they are also supposed to do some introductory course in linear algebra in their college or university where they have been graduated from. But however, it is realistically speaking, we do have students from various backgrounds, students who are trained in various institutions all over the country by various people. So, therefore, what I think is it is not reasonable to assume anything. So, I would rather prefer to start from the scratch. So, I will start with system of linear equations and then go ahead in the usual way in which the subject goes. So, the first few lectures what I am going to cover, some of you might find that a mere repetition because you might have seen those topics. So, I apologize for that, but however, those who are not confident in those material, in those topics, and or even if they have seen, they do not feel comfortable. So, I would suggest them to pay careful attention because this is the chance where they can learn those things once again. So, let me start. So, as I said, I will start with system of linear equations. So, what I am going to discuss today and mostly in that course, what I am going to discuss, so that goes over any general field, but however, in order to make things simpler and also keeping in mind that many of you may not be comfortable with general fields. So, I will throughout assume my field is either Q or R or C. Okay. But as I said, whatever I discuss that goes, whatever I discuss, mostly everything goes without any difficulty for any general fields. Okay, let me start, that is better. So, I will start with a system of linear equations. So, let F be my field. So, by a system of linear equation, I have a set of equations, let us say m equations in n variables, which looks like this. A m1 x1, a mn xn equal to y m, where aij lies in F. As I said, you may assume F is either rational either set of rationals or reals or complex numbers for I from 1 up to m and j from 1 up to n, and then also y1 up to im, they also belong to F. So, this is my system of linear equations. So, what I will do is the material what I am going to cover in the first few lectures, since many of you either have mastered them or at least seen them before. So, therefore, I will cover them thoroughly but quickly. Okay. So, this is what my system of linear equations, this system of linear equation is. By a solution of this system, I mean a tuple in Fn which So, if I label this system as star which satisfies all equations in the system star, all in star. Okay. By a solution I mean a tuple. So, our job is to solve a system of linear equations. So, given a system of linear equation, we want to solve it, that is we want to find all possible values of this the tuples which satisfy this system. Okay. So, the most fundamental technique for solving a system of linear equation is the elimination, or some people call it Gaussian elimination. So, what do we do in that what do we do there? What we do is we multiply the equations by some suitable scalars. Here scalar means members from the field from which the coefficients are taken from. We multiply each equations by some suitable scalars and add them in such a way that some xj will no longer be present in that in that new equation. So, therefore, thus we have reduced the system by one variable, okay. And once we keep on doing that, so eventually we will come to the simpler situations where we have only a few variables, so that there we can solve. So, let me formalize what we do in the method of elimination to understand what is going on, to understand why that method works, and also to be able to use that method later on whenever necessary in a more organized way. Okay. So, let us do that. So, as I said, we will take scalars. So, in the method of Gaussian elimination, what we do is we multiply the equations by scalars. So, if we multiply the first equation by the scalar C1, multiply the second equation by the scalar C2, Cm, that becomes equals to C1 y1 plus Cn yn. So, we can rearrange the terms in the following way, that is I would like C1 a11 plus C2 a21. So, C1, so basically we will vertically we have m such terms corresponding to x1. So, we will add their coefficients together. So, thus we have C11 a11 plus C1 a11 plus C2 a21 plus Cm am1 x1. Similarly, C1 a12 C2 a22 plus Cm am2 x2, so on and so forth. What we get towards the end is C1 a1n, so on and so forth, Cm into amn xn. Okay. So, multiplying the first equation by C1, second equation by C2, and so on and so forth, multiplying the mth equation by Cm and then adding, this is the equation that we get. Yeah. Okay. Now, it is easy to see that if x1 up to xn is a solution of this system, that is if that satisfies all the equations, then the x1 up to xn will satisfy this new equation as well. So, that tells me the following, that suppose from the given system star I construct a new system whose all equations are combinations of the equations of star, then well, let me write that better. So, I am writing it here. So, suppose I from this system I form another system of equations such that B1n xn equals to let us say Z1, and we'll let this system has k equations, but the number of variables is same as that of star Zk. So, let me label this by double star. If this system double star has the property that every equation in this system double star is obtained by considering combinations that which we customarily say linear combinations. If every equation in this new system is a linear combination of the equations of this system, then every solution to this system also is a solution to this new system double star. Okay. But yeah, one point is there, that as I just said, that every system here, that is also every solution here is also a solution there, but the question, but there could be some solutions of this system here which may not be obtained from which there might be some solution of this system which is not a solution of the system that we have started with. This can be there, because I mean that depends, you don't, I mean in general these equations can be formed in some arbitrary ways. So, there is no reason to expect that any solution here also is a solution there. Okay. For example, let me tell you, I mean in principle, as I said that I am allowed to consider any combination. So, if I choose all Ci's to be 0, then the system is a 0 system. So, here any tuple, every tuple in Fn satisfies that, but certainly this may not have those many solutions. Okay. So, let me again repeat, starting with a system where suppose we start with a system which has I mean whose solution set of all solutions is a proper subset of Fn, but from that system if we just choose scalars, all scalars to be 0 and consider the linear combinations here, then the new system will have this as its set of all solutions. So, the point that I am going to say that this system might have more solutions than the original one. Okay. But suppose the system, this new system, suppose that this new system has been formed in such a way that any equation in the original system is some linear combination of the equations in the later system double star. I repeat that suppose I have constructed this system in such a way that it is reversible, that is any equation here is also some combination of the equations of the system double star, then naturally any solution here is also a solution there. So, thus we see that the two systems have precisely same solutions. Okay. I repeat, given a system of equations star by considering linear combinations of the equations in star, if I construct a system, if I construct another system of equations, then this new system, then every solution of the older system is a solution to the new system. Furthermore, and this new system might have more solutions, but furthermore if I construct this new system in such a way that it is reversible, that is from these equations, from the equations of this new system I can get back the original get back the equations in the original system by taking linear combinations, then any solution here is also solution there. Hence the two systems star and star double star will have exactly the same solutions. Okay, so let us introduce a terminology. If two system of linear equations have same solutions, then we will call them equivalent. The system is said are said to be equivalent if they have same solutions. Okay. So the reason for starting with a given system, the reason for passing through a new system which is equivalent to original one is now very clear. As I said, our aim is to, given a system of equations, we want to solve it, but the way the system is given in the beginning, it might be very complicated to solve that. So what we do is, by considering combinations, we will pass to a new system, which is passed to a new system, which is and in fact an equivalent system, which is simpler to solve. That is what the main reason for passing through an equivalent system is. That is, we will try to simplify the system, and also that is to be done in a way that neither we lose any solution nor we gain any other, neither we lose any solution of this system nor we gain more. Okay? Fine. So that is how we define equivalence of two system of equations. Now let us observe one thing very carefully. When we consider, suppose this is my system, I am given with, when I consider the combinations of the equations in the system, then one thing that I can observe is this variables x1 up to xn, they are not actually playing any role apart from fixing the positions of the coefficients aij. So let me clarify that what I mean by this. That is, suppose if I take the combination of these two equations, that is C1 A11 x1 plus C1 A12 x1 x2 plus Cn A1n xn C1 y1, and then with that I add this C2 sorry. So then you see that I cannot directly add this term, this C11 A11 to some Cj to j, okay, because what we are doing is we are collecting all the coefficients of x1 and then adding them together. Okay. Directly I cannot add the coefficient here with a coefficient from some other term. So basically the role that is being played by this variable symbols x1 up to xn is precisely fixing the positions of the entry of the coefficients, right. I mean because of x1, so its position is fixed, I can only add these two, that is what I mean. So hence, since the variable symbols x1 up to xn are not playing any other role than fixing the positions of the coefficients. So, therefore, it is convenient to use the matrix notation instead. So, what we will do is we will write it as A x equals to B, where A is the coefficient matrix A11, A1n, An m1, Am n, and B is the matrix 1, 2, m, okay, and x is the. So, this is just a, so this is just a symbolically I write x1 up to xn as a column vector. So, given a system, this A is called, given a system of equation. So, the matrix formed by the coefficients of that system is called the coefficient matrix. Coefficient matrix of the system, and we also have another terminology here. So, we will make another new matrix where it will be a, so this coefficient matrix has order m by n. Okay. So, we will form another matrix of order m by n plus 1, which is basically the first. We will keep all the coefficients of this system, and in the last column what we do is basically with this matrix we will add one more column, and the last column is going to be the vectors y1 up to yn. Okay. So, we usually write it as A, B, yeah, and called it augmented matrix associated to the system star. Okay. So, as I said that it is convenient to use this matrix notation because precisely because that we have seen while taking combinations, these xi's are basically fixing the positions, so that nothing from here can be added to something from something attached to some other xj. So, therefore, it is convenient to use the matrix notation instead. Okay. So, now once we have decided that we will be using the matrix notations for system of equations, then something very interesting we can observe. So, suppose star is a system, and from that by considering linear combinations of the equations of star, I have formed another system double star. So, let me for this system let me write the coefficient matrix as A prime and the augmented matrix as A prime B prime. Okay. So, given a system of equations star, once by considering linear combinations I arrive at a system arrive at a new system double star, then we will see the matrix of this new system and the matrix, the augmented matrix, I mean the augmented matrix associated to the older associated to the original system, they have some important connection. So, what is the connection? I will show you now. So, remember we have obtained this system by considering linear combinations of the equations of the original system. So, therefore, if you see, so suppose the first equation is formed in the way that I consider the first equation, I multiply the first equation of the original system by C1 and the second equation by C2 and blah blah blah, the the last equation by Cm, then so what happens is, so B11 is nothing but, so let me rather write it in a much more convenient way. Suppose the first equation is from the original system, the first equation has been formed in the following way, that is I multiply it by C11 C11 well, let me write it in this way, A12 x2 A1n xn equal to C11 y1 plus 2 1 and then similarly we M1 1 to 1 M 1 M, yeah. So this will be A M1 x1 plus A M2 x2 plus A Mn xn to C M C1 M y M, or more generally we can do it for any ith equation. So, for any I from 1 up to k, suppose this ith equation of the new system has been formed by this, where Ci1 up to Cim are from F. Okay. So, I repeat, what I am doing is, suppose the ith equation for any I, for any general I of this new system is formed from the older system like this, then what is going to be the coefficient matrix of this new system? Coefficient matrix, or in fact the augmented matrix. If you see, the ith row of this augmented matrix A prime B prime is nothing but the following Ci1 into, so A11, A12, A1n, they lie in the, they are in the first row of this matrix. So, C11 into the first row, then Ci2 into the second row, and going similarly Ci yeah, I from 1 up to k, Cim into the last row. Okay. So, again what I am doing is I am looking at the ith row of this new augmented matrix, that is nothing but the multiplying the first row by Ci1, multiplying the second row by Ci2, and similarly going on and continuing like this, similarly multiplying the last row mth row by Cim. This is going to be my ith row, which is Bi1 Bin. So, this for any I to k. So, like, does this remind you something? Let me rather write like this. So, this sum is equals to this. Does that remind you something? Yes, that is very clear that the system, the augmented matrix. So, when do you see such things? That is the by a constant you multiply the first row of some metric, then some other constant, multiply the second row, and continuing that multiply the last row, and then you add everything. We find this when we multiply to matrices, right? Exactly. So, therefore, the augmented matrix of the new system is obtained by multiplying the older augmented matrix by some matrix for some m belonging to, well, I should not use the m. So, instead of m, let us rather use some ABC, some let us say d, for some d belonging to m. So, so this d has k number of rows and k number of rows and m number of columns, right. So, what I have observed is, if from a given system star I construct a new system double star by considering the linear combinations of the equations of star, then the augmented matrix of double star is obtained from the augmented matrix of star by multiplying by some matrix having k rows and m columns and having entries from F. So, multiplying this matrix by some matrix here from the left. Okay. I repeat, what we have seen is, suppose from star to double star, from star to double star, from star we've constructed a double star by considering combinations, then their augmented matrix of the double star will be just the augmented matrix of the star of the system star multiplied by some matrix from the left. I leave you to verify that the converse also holds, that is, suppose for two systems star and double star, their augmented matrices are related like this, then this the system double star is indeed obtained by considering combinations from the combinations of the equations belonging to the system star. So, thus like we have seen that taking linear combinations is same as multiplying by some matrix from the left side. Okay. Let us go ahead. Okay. So, let us see the following. Again, you have to remember what our aim is. Our aim is to solve a given system of equations. So, how do we solve? So, the way the system when it is given in the beginning, it may be in such a complicated form that we can't see any solution just by inspection. Then what we do is, we would like to transform the system to a equivalent one which is simpler to solve. Okay. And in terms of matrix, we would like to multiply the augmented matrix of the system by some suitable matrix, so that I can arrive at a equivalent system whose matrix is relatively simpler from that what are given to us, what were given to us in the beginning. Okay. So, what we will do is the following. So, if suppose two systems star and star double star are related like this, if D is equivalent, D is the matrix given here is non-singular. So, what I mean is, well, let me put it as a theorem. So, if in order to be non-singular, k have to be equal to m. So, if k equal to m and D is non-singular, a better way to put that is invertible. So, what I mean by an invertible matrix is, there exists another square matrix of the same order D prime, such that D times D and D times D both are identity. Okay. Fine. So, there is an, if D is invertible, then the systems are equivalent. Equivalent. Why? That is very easy to see. Again, you have to remember what I mean by two systems are equivalent. So, given a system, from that, you considering linear combination, we arrive at a system. If the new system and the older system, they have exactly same solutions, then we will say that those two systems are equivalent. So, here suppose this is the matrix associated to the system double star, and this is the matrix with associated to the system augmented matrix, I mean system star. If the matrix D, that which this matrix, you have to recall that this matrix is composed of the scalars which are used to construct these equations in the new system. Okay. So, if D is equivalent, if D is invertible, then the systems are equivalent. So, in order to prove they are equivalent, what we have to do is we have to show that they have same solutions. So, that is very easy to see. So, suppose like we have already proved that when from a system we construct a system by considering new linear combinations, then any system, any solution to the original system is a solution to the new system. So, now in order to prove the equivalence or prove that they have the same solutions, I have to show that any solution here also is a solution there. So, that is very easy to see. So, any solution of the later system. So, as you let x1 up to xn be a solution of the later system, let us call it x1 x1 prime. So, yeah, let this be a solution of double star. Okay. That means, so if I denote this by the write it as a column vector, which we always do, then what we have is A prime x prime is equals to B prime. Okay. Now, multiply both sides by D inverse. So, D inverse A prime x prime equals to D inverse B prime. Then you apply the associativity of matrix multiplication. Okay. So, what is D inverse A? D inverse A is just, so D inverse A prime is A. Similarly, D inverse B prime is B. So, this is the Ax equals to B, Ax prime equal to B. Okay. So, that shows any solution, if D is invertible, then the systems are equivalent. Okay. So, therefore, so in view of this theorem, it is now quite clear to us that our attempt should be in finding a suitable D that makes this system simpler, so that we can solve. Okay. Now, I will introduce a terminology. So, given a matrix, any matrix A, let us say m by n matrix, given a matrix A, multiplying this matrix by an invertible matrix from the left, if A E is an invertible matrix, E is an invertible m by n matrix, E is invertible. The multiplication of a given matrix by a invertible matrix from the left is is given a very special name, which is as follows: row operations. Okay, I repeat, the process, the act of multiplying a given matrix by an invertible matrix from the left is also called row operation, row operations. So, in with this terminology, so we can rephrase what we have just said a few minutes back, that is, well, before that let me give you some justification for behind this nomenclature. If you have if as we have realized that multiplying a given matrix, when we multiply a given matrix by some other matrix, let us say we multiply A by B, then what we do is, what is the ith row of this product? Basically, this is the linear combination of the rows of A by the scalars which are appearing in the along the ith row of B. So, since when we consider the product of two matrices, then what we actually do is we consider the linear combinations of the later matrix by the coefficients from the former one. That is why, so basically since we actually operate the rows, that is why this name has been given to that process. Okay. So, as I said, in view of this new terminology, we will rephrase what we have said a few minutes back, that is, given a system, what we will do is, by operating rows of the augmented matrix of the given system, we would like to arrive at a simpler matrix from which we can easily solve the system. Okay. So, as I said that I want to pass through an equivalent system which is simpler, and that will be done through row operations. Okay. Now, what I will do is, I will tell you three fundamental types of row operations. Fundamental in the sense that any other row operation we can achieve by these three fundamental row operations. Some textbooks, some authors call it elementary row operations. So, let us stick to that. So, we will talk about three fundamental types of row operations, which we will refer from now on as the elementary row operations. So, the point is, any row operation we will shortly see, maybe not in this lecture, in the next lecture we will show that any row operation can be achieved by these three elementary by these three fundamental types, using them at our will as it turns out to be necessary. So, I repeat, any given row, the three row operations that I am going to tell you, they are from these three types you can achieve any other row operation by applying them again and again as necessary. So, what are the three types? So, let us first consider type 1. I have to mention the matrix, right, because row operations means multiplying by an invertible matrix. So, for type 1 the matrices will be of this kind. So, let me write down the matrix for general n by n order. So, along the diagonals all the entries will be 1, and some off diagonal entry may be above the diagonal or below the diagonal will be some non-zero constant. I repeat, and 0 elsewhere. So, basically in the identity matrix we choose some off diagonal position and put a non-zero constant there. Okay. So, this is so for any such non-zero constant I have two such matrices. So, thus I have so many matrices of the first kind. So, as I said that we have already observed that once we multiply by an invertible matrix, once we multiply not only invertible, multiply a matrix from another matrix from the right. So, that operates rows of the later matrix. So, let us first see what operation this kind of this first type of matrices do with any other matrix when we multiply the given multiply that matrix by a matrix of this form. So, let us see that first. A1, suppose this is what my given matrices. Well, I do not have to, rather I can write row wise. So, suppose R 1 up to n or m are the rows of a given matrix A, and I multiply a given matrix A by a elementary matrix of first type. So, let us say sum of diagonal entries this constant non-zero constant A. Okay. What will be the matrix? It is easy to see that. So, the first row here is 1 0 0 0. So, the in the product the first row will be precisely R 1. So, it will go like that until suppose this is the ijth position, ith row jth position. Here something will be changed. What you do is here at the iith position you have 1. So, when you consider the combinations, as we have already seen that when we take the product of two matrices, the ith row will be the combination of the ith row, combination of the rows of A having coefficients from the ith row of B. So, here when you consider the combination, so 1 will be multiplied to the ith row of A. So, that is it will be R I, but you will not stop with that. When it will you go ahead, then since at jth position A is there, so A will be multiplied to the jth row of A. So, that will contribute A I plus R j, and then it is easy to see rest of them, rest of the rows will be exactly same. So, thus as I said, thus the the operation that the first type of elementary matrices do on a given matrix is we multiply the jth for if this is my matrix which has A at the ijth position, then for any other matrix when you multiply that matrix by this elementary matrix, what it will do is it will only change the ith row of the product, ith row of this matrix, and the ith row will be changed as ith row plus A times jth row. Okay. Since I do not have much, I am running out of time. So, I will rather suggest you to write some concrete example, suggest you to compute some concrete examples and convince yourself. I will quickly tell you about other two elementary matrices, and with that I will stop. What is the second type of elementary matrix? That is given by, so what we will do is let us fix I and j. So, again it will be identity matrix except the ith row and jth row of the identity matrix, suppose I have changed them. Let me again repeat, if you come back to the first matrix. So, how is this matrix formed? So, this is basically in the identity matrix, what we have done is we have multiplied the jth row of the identity matrix by the non-zero constant A and added that to the ith row. So, this matrix is formed by multiplying the jth row of the identity matrix to the and adding that to ith row, and when I multiply a given matrix by such a matrix, the same thing goes here in the sense that it also multiplies the jth row of the matrix we have started with by the constant A and add that to the ith row and keep other rows intact. So, here also, so this second type matrices are obtained by for any ij I not equal to j, we just flip the ith and jth rows of the identity matrix. So, and this is 1 1 0 elsewhere. Okay. So, for any ij I not equal to j, we flip the ith and jth rows of the identity matrix, and it is easy to see when I multiply a given matrix A1 up to A whose rows are R1 up to Rm by a matrix of this form, then what it has done I mean the way by the operation which has been used to obtain this matrix from identity matrix, actually the same physical operation goes, the same physical operation applies to the rows of the matrix A, which I am multiplying by this. So, the rows of this new matrix will be only other rows will be same except ith and jth row. The ith row of this new matrix will be the jth row, and the jth matrix row of the new matrix will be the ith row of the original matrix, and rest will be same. So, in the informal sense or in the physical sense, the operation that has operation applying which on the operation applying on the identity what gives me this matrix, that operation, that physical operation applies to the any matrix when I am multiplying the matrix by a matrix of this kind. Okay, I hope my point is clear. I am slightly going in a hurry. So, therefore, as I said, I will suggest you to first of all, I assume that these are the things that you have seen earlier. So, it is better that you revise it once again by writing some concrete examples and making computations. I will just finish with the third type, type 3. What are the type 3 elementary matrices? These are also very simple matrices. So, on the identity matrix, multiply some row of the identity matrix by a non-zero scalar C, multiply some row for any for any I 1 up to m and any C belonging to the field. I have these many different elementary matrices of type 3. I repeat, how we obtain the matrix is we multiplied the ith, let us say the ith row of the identity matrix by the constant C, and as usual when I will multiply a given matrix by this by a matrix of this kind, then it will result into the change into the following change, that is the all other rows except the ith row will be unchanged, and the ith row will be changed by C times the ith row will be just scaled by the constant C. Okay, I will finish. Before that, let me just again remind you what these matrices are doing. So, I mean for all three types of elementary matrices, the matrices are, you can regard them, the matrices are constructed by doing some operations on the rows of identity matrices, and for any such matrix, when you multiply a given matrix by such a matrix, then the same operation actually applies to the rows of the given matrix. Therefore, the product apart from the rows where I have made the change in the identity matrix that I am using, all the other rows of the later matrix will be same, and the rows where we have the elementary matrix, the rows where we have made the operations, only those rows will be changed in the later matrix exactly in the way exactly following the same operation which has been applied to the identity matrix to obtain the elementary matrix that we are multiplying by from the left. Okay, I think for this lecture is enough, so I will stop. Thank you.